yeah, as said, what I want to talk about today is Gaussian process regression, in particular kind of convergence and robustness properties of Gaussian process regression. So the outline of my talk is the following. So I'm going to start just by introducing the problem that I'm interested in solving. And I'm going to tell you how to solve the problem using Gaussian process regression. So this is a methodology that is very commonly used in statistics and engineering in very many different applications, also climate modeling. It's a very popular methodology. And what the talk is about is kind of more looking at this methodology from a mathematical, from a kind of numerical analysis point of view, and looking at what kind of convergence properties this has. And then in the end, I'm going to talk a little bit about applications of this methodology in Bayesian inverse problems. So if there are any questions in between, then please type them in the chat, and if I see them, then I'll try to answer them. But I'll try and leave plenty of time for questions in the end as well. Right. So what is the problem that I'm interested in solving? The problem that I want to solve is this one. So I assume that I'm given n function evaluations. So I have this data y, which consists of some function values of some function f. So I assume that I have some underlying function f that just maps from some domain u into the reals. You can deal with other image spaces as well, but here I'm going to just consider scalar real valued functions for simplicity. And I want to kind of learn or recover what this underlying function f is given this data in the term of function values, right? So I have some input values un, which are just some points in the domain of f, and then the corresponding function values. Okay. So this maybe sounds like a very simple problem and not a very interesting problem, but it's actually neither. So it is a problem that appears in very many different applications. So for example, in machine learning applications, you very often have this problem where you're given some training data, which would look like this. So you have some input-output pairs as your training data. And then what you want to do is you want to predict the output for different values of the input, which essentially means that you want to recover this function f that is generating the data, and that's mapping the input to the output. It's also not a very easy problem to solve. So if you don't really know anything about the function f, and the function f can be completely general, then this is actually a very difficult thing to do. So your function f could be a multi-scale function. It could vary on many different scales. You could have very steep gradients in f, or f could just be a very rough function, so it could not be differentiable and things like that. And so when the function f is completely general, this is really a very difficult problem to solve. Okay. So that is the problem that we want to solve. We're going to solve it in a statistical framework, in particular a Bayesian statistical framework. What that gives me as a result is a probability distribution on my unknown function f, given the observed data y. In particular, in the Bayesian framework, this probability distribution is called the posterior distribution, posterior measure. Okay. So what that allows me to do is to have some uncertainty quantification in my recovery. So it doesn't just tell me something about what I think f is, it also tells me something about how certain I am what f looks like. Okay. So you can think of this probability measure that you have here. If you look at the mean or the mode of this posterior, then that gives you something what kind of a best estimate for your function f. And then you can also look at the variance in this probability distribution. So whether you have something that's quite broad or whether you have something that's really quite peaked and concentrated on a particular f, then that tells you something about how certain you are about your recovery. Okay? So you get a full probability distribution on your unknown f. So the question that I'm going to be interested in the talk is what happens as n tends to infinity. And so what you hope is that as n tends to infinity and you have more and more data and you have more and more observations on your function f, then the hope is that you kind of are able to recover the truth. And so recover the true underlying function F. So that's a concept that's sometimes called posterior consistency. And in particular, what we're going to be looking at is whether the mean of this probability distribution that we have on F given Y, whether the mean of this converges to the true F, and whether the variance of this goes to 0. Right? So as n tends to infinity, we're kind of going to recover the true F, going to converge to the right thing, which means that the mean converges to F, and we want to be really sure what the function F is. And so we want the variance to go to 0, and so this probability distribution on F given Y kind of just converges to a peak, like a Dirac at the truth. Okay. So that is the general setup. So what is now Gaussian process regression? So Gaussian process regression is just a particular example of this Bayesian statistical framework. And in particular, it corresponds to a particular choice of the prior distribution. So as I said, Gaussian process regression is a Bayesian methodology. So the way that it works is in the general kind of Bayesian setup that you choose a prior distribution on your unknown F, and then you update the prior to the posterior by conditioning on the data. Okay. So the first step is to choose a prior distribution on your unknown F. How you choose this depends a bit on the function, and I'm going to get back to that later because it's an important point. But you should choose your prior so that it kind of reflects things that you know about F, right? So you might know that F has, I don't know, one or a derivative or two derivatives or things like that, and you can incorporate that into the prior. But as I said, I'm going to talk more about that later on. Okay. If you don't know what a Gaussian process is, or if you're not that familiar with Gaussian processes, I've given you the definition here. Okay. So a Gaussian process is a stochastic process. So it is a random function. So you can view this Gaussian process prior as a distribution on functions. The function f is a Gaussian process. That means that at any point ui in the domain of f, f of ui is now a Gaussian random variable. And in particular, any finite collection of points f of ui is a multivariate normal. So it's a multivariate Gaussian variable. The mean of this Gaussian variable is given by the mean function. So here we've chosen mean 0. That's the first argument here. And the covariance between the points is given by this covariance function k here. So you have this equality here. And so it's the mathematical definition. Visually, it looks like this. So you choose some mean function, which here we've chosen to be 0. So just have a constant mean 0. And then you also have some standard deviation at every point, which here is just 1. And so if you look at sample paths or realizations of this Gaussian process, you get functions that look like something like this, right? So they stay close to the mean, and then they fluctuate around the mean, where the fluctuations in size are kind of proportional to the standard deviation that you've chosen. Okay? So under this Gaussian process prior, your f looks something like this. And as I said, it's just a probability distribution on functions. Okay. So once you have this prior distribution, as I said, you then do the standard Gaussian, the standard Bayesian prior to posterior update. So you get the posterior distribution on f conditioned on the observed data just by conditioning the prior on the data y. That again gives you a Gaussian process. So that comes from properties of Gaussian random variables, and under conditioning, you then still get a Gaussian random variable. So that is also true for Gaussian processes. So you know that the posterior is a Gaussian process, and you can in fact also write down explicitly what the mean and the covariance function of these Gaussian processes are. And so I've given you the formulas here, and some of you might be familiar with these formulas, but exactly what they are is not really important. So the only important thing is that you can write these down explicitly. And so this posterior distribution that you get here is known analytically, so you know explicitly that it is Gaussian with a given mean and covariance. Okay. Visually, again, it looks something like this. So you have now an updated mean. So you have the mean that there's now this black line here. The black dots correspond to the data that we have observed. So I'm here assuming that we have observed these black points here. And you can see by conditioning on going through those points, you're updating the mean. The mean will go through these points because you're conditioning your distribution on passing through the data points. And then you also have the updated standard deviation function, the variance function. And you can see that at the points, the posterior covariance is actually 0. And that's because here, I mean, there's no uncertainty what your function is doing here, right? You know that it goes through this point. So at all the points you have 0 variance, whereas in between, you're still a bit unsure what the function is doing and what the function is. So you have a larger range for the variances in between. Yeah. And again, you also get updated sampled paths or realizations of the Gaussian process posterior. And again, you're conditioning on going through these points. And so all of your points will, all of your sample paths will now sample through those points. And these are the samples from the posterior. Right. So as I said, you can actually write down this Gaussian process posterior analytically, so you know what it is in closed form. That is one of the big benefits of Gaussian process regression, that you can actually do this conditioning completely explicitly. So that's one of the reasons why it is used so much. Right, but as I said, the way that you choose the prior distribution is actually very important. Right, so I've shown you in the last slide that once you have your Gaussian process prior, getting from the prior to the posterior is quite straightforward. You have your formulas that you can use to update the prior to the posterior, but how you actually choose the prior is very important. So that's something that you always have in Bayesian methodologies, that you do need to choose your prior in a sensible way to get a kind of a sensible posterior distribution as well. Right. And in particular, the way that you need to choose the prior is you kind of need to choose it so that you capture the correct properties of your unknown function f. Right? So what do I mean by properties? By properties, I mean these things that I've listed here. Okay. So in the prior, we've chosen mean 0. You can also do non-zero mean, and I'm happy to talk more about that later on if people are interested. So everything is kind of determined by the covariance kernel that we've chosen. So it's the covariance kernel K that kind of determines all of the properties of the Gaussian process and the sample paths. So one important property is what I call smoothness. So there's this really differentiability. So by smoothness, I mean how many derivatives do my sample paths have? Okay, so I've given you a couple of examples of Gaussian processes here. So all of these graphs show 5 independent sample paths from a Gaussian process with different covariance functions. So all of these 4 graphs have different covariance kernels K. Yeah. So in the top row, I've chosen a covariance function that gives you sample paths that are not even differentiable. So they are continuous, but not differentiable. If you're familiar with this area, I've chosen the exponential covariance function. So that's the covariance function of the Ornstein-Uhlenbeck process. Yeah. And you can see that they look quite rough. And in the bottom row, I've chosen a covariance function that gives you C infinity sample paths, so sample paths that are infinitely many times differentiable. And you can see that they do look a lot smoother. And again, for those who are familiar with the area, I've chosen the Gaussian covariance function, or the squared exponential. So that is a very smooth covariance function. Okay. There's also something called the contrast. So contrast is really the marginal variance. So that would be a parameter that tells you how big the oscillations are. So kind of whether you go between -4 and 4 on the y-axis, or between -40 and 40. So it's kind of the kind of height of the oscillations. Then there's another thing which is called length scale or length scale fluctuations. So this is the correlation length scale of the Gaussian process. So this is typically denoted by some parameter lambda. And yeah, it's the correlation length scale. So it's the length scale at which 2 points are correlated. If this lambda is quite large, then you get sample paths which look something like the left column. So you have functions which vary more on longer length scales. Whereas if the lambda is quite small, then you get something that varies on much shorter length scales. So you can see that this right plot here, is much more oscillatory and varies on much shorter length scales than the one to the left here. Yeah. So these are properties of the smoothness, contrast, and the length scales. These are typically all kind of hyperparameters that appear in the covariance kernel and that you then have to choose. Right. So there's also other properties such as periodicity, so whether you have periodic functions, stationarity, whether your function kind of behaves the same everywhere in the domain or whether it behaves differently in different parts of the domain. But I'm not going to be talking too much about those today. Okay. So the challenge is now that these hyperparameters, so the parameters that govern the smoothness, the contrast, and the length scale, are typically not known a priori. Right? So to know the hyperparameters, you would have to know what kind of properties your function f has. So is my function f smooth like here, that it only varies on long length scales, or is it more oscillatory? And the problem is you don't know these things, right? The f is unknown. The only thing that you know about f is these function values that you have. And so these kind of properties are just not known a priori, and so they're difficult to choose and to specify in the prior distribution. So you somehow have to find a way of kind of incorporating that into the methodology. So the fact that you don't really know what the hyperparameters in the prior are, or that you don't know what prior you should choose, you have to somehow find a way of incorporating that into the methodology. Okay. So you could do a fully Bayesian approach, so this hierarchical Bayesian approach, where you would obtain the posterior that you're interested in on f given y by first finding the joint posterior of the unknown f and the unknown theta given y, and then marginalizing out the theta, so integrating over theta. However, that is very often very expensive. So doing this integral over theta can usually not be done analytically, and doing it numerically would be very expensive. So an alternative to this is that is often used in practice because it's computationally more tractable, is empirical base. So in empirical base, what you do is you use your data, which is all that you know about your function f, and you use that to estimate a value for the hyperparameters. So that gives you an estimated value theta hat n. And then you kind of just pretend that that is the true value of the hyperparameters. And so you just plug that in to your prior distribution and then do the standard prior to posterior update. And so you use the data to estimate the hyperparameters and then pretend that that estimated hyperparameter is the kind of true value for the hyperparameters. So how you get the estimate of hyperparameters is also a difficult question, and there's still a lot of research going on in that direction. I'm not going to talk too much about that, so that is kind of a separate issue. You can use maximum likelihood or maximum a posteriori estimation or cross-validation. Those are typically often used. As I said, it's kind of a whole research area on its own. So what I'm going to be interested in is, as I said in the beginning, kind of the posterior consistency aspect. So what happens as n tends to infinity and I have more and more function values of f? And in particular, does the fact that I have to estimate these hyperparameters and that this estimate of the hyperparameters then also changes with n, how does that kind of influence what happens as n tends to infinity? And am I still able to get posterior consistency? So am I still able to recover the true function f in the end? So that is what I'm going to be focusing on in the next couple of slides. All right. So as I said, what I want to do is look at what happens as n tends to infinity. And in particular, I want to show you some convergence results. So these are results that are kind of more of a numerical analysis flavor, looking at what happens as n tends to infinity. And in particular, what we wanted to show is that the mean of our posterior, so the mean of f given y, tends to the true function f, and the variance of the posterior, so the variance of f given y, the uncertainty in f given y, tends to 0. Okay, so that was what we wanted to show. So to do that, we can make use of the explicit expressions that we have. So remember, I told you we do have explicit expressions for what the posterior mean is and what the posterior variance is. And in particular, if we look at the posterior mean, we can see that it has these two properties. Okay? So the first property is that at the points where we have observed f, so remember these UNs where the points that we have where we have observed f, at those points the mean goes through or it interpolates the true function f, right? So that was just these pictures that we had here, right? So at the points where we have observed our function f, because we're doing the conditioning, we know that the mean goes through the points. Right. So it's just this. And then another thing that you can see from the explicit expression for the mean is that it has this form here. So you can show that it is a linear combination of the prior covariance kernel that you chose, right? So the K was the covariance kernel in our prior, and you can write the mean in this form here, where the coefficients are known. So you can write down the explicit expression for that as well. Right. So why is that interesting? So it tells you that the mean, so this tells you that the mean is an interpolant of f, and this equation here tells you what the basis functions are, right? So when you're looking at interpolation, you can use very many different types of basis functions. You could do polynomial interpolation, for example, but what you end up doing here is an interpolation of the function f in basis functions, which are given by the prior covariance kernel, right? So that's what written here, that the mean of the posterior is what is called a kernel interpolant of f, just means that it is an interpolant of f, and the basis functions are these kernel functions, right? So that is then very much related to radial basis function interpolation, which is a very well-known method from numerical analysis. Okay. So that happens when you have the particular case of isotropic kernels, when so the covariance kernel depends on u and u prime only through the distance, but that's kind of more of a side note. Right. So I think now you can kind of already see where the convergence estimates and the error bounds would come from, right? We know that we're essentially just doing interpolation in a particular set of basis functions. And so what kind of rates and what kind of convergence properties we get will depend on the specific choice of prior, so on the specific choice of k, because k is what acts as the basis functions in this interpolation. Okay. So there are very general results out there. So kind of whatever your favorite covariance kernel is, there should be some results out there that tell you what kind of convergence properties you have and kind of what kind of convergence rates you get and what sort of assumptions you need on your function f for this to work. So what I wanted to do now is show you one particular example. So there's one particular example of k that is very often used. And so I'm going to show you how the error bounds look for this particular k. Okay. So this particular k is the family of Matern covariances. So as I said, this is a parametric family that is very often used. So it has 3 hyperparameters. So there's the parameter sigma squared, which is the marginal variance or the contrast, this is the hyperparameter that governs how big your oscillations are. And then there's the parameter lambda, which was the correlation length scale. So that was telling you whether you have quite smooth functions that vary on long length scales or very oscillatory functions that vary on shorter length scales. That was the lambda. And then the final parameter is the nu, which tells you the smoothness, so how many derivatives you have. So whether your prior distribution gives you C1 functions, so once continuously differentiable, or C infinity functions, or something like that. So that is what the nu tells you. So the general formula looks quite complicated. You can see it involves the sigma squared, the lambda, and the nu. So the gamma here is the gamma function, and B nu is the modified Bessel function of the second kind. It does simplify in some special cases. So when the nu is equal to 1/2, it simplifies to the exponential covariance function. So you get this. So this is the covariance function of the Untitled process in one dimension. And here, when u equals infinity, you end up with this squared exponential or Gaussian covariance function. So those are some of the special cases that you get. It does simplify for some other expressions, for some other values of nu as well. Right. So this is the k that we're going to work with. It is very often used just because it is a very flexible class of prior distributions. So prior distributions covariance kernels. So the nu, lambda, and sigma squared, you can all choose them anywhere between 0 and infinity. And so by varying them on different scales, you can really get very kind of different types of functions. And so it kind of encompasses a very big range of scenarios. Right. So this is a horrible slide with a lot of technical details, but let me try and walk you through kind of the main points. So this is now a error bound that tells you something about the convergence and what happens as n tends to infinity. Right? So it is for the particular case where we're using the Matern kernel, and we are estimating now the hyperparameters. So the theta n hat are now estimated hyperparameters, and the theta is sigma squared lambda and nu. So the theta here is a vector of length 3 that encompasses these 3 hyperparameters. You have one result that shows you that the mean of the posterior converges to the true function f. Right? So this right-hand side here should go to 0. So you can see that the mean of the posterior tends to the truth as n tends to infinity. And then you have a result on the variance, or here the standard deviation. And this shows you that the variance of the posterior goes to 0 as n tends to infinity. Right. So what do we have on the right-hand side? So on the right-hand side, we want to have this norm of f. So this result assumes that f is in this space. So this is a Sobolev space. If you're not familiar with Sobolev spaces, this essentially means that we're assuming that my function f has this many derivatives. So we're assuming that it has nu plus d/2 derivatives, and these derivatives are square integrable. Right? So they don't have to be continuous, but they have to be well behaved in a certain sense. So we have this many derivatives that are square integrable. So that's one assumption, that we need our f to be sufficiently smooth. And then we have these two terms here. So here we have these two terms that depend on n. So this is where the dependency on the number of points n comes in. The first one is the one that kind of gives us convergence as n tends to infinity. So the quantity that we have here is the so-called fill distance. So it's also called the separation radius or the maximum distance. I think in statistics it's called the maximum distance. It's defined in this way. And so if you look at the set of points where you have observed f, which is this set of design points, and then you look at any point in U, and then you look at how far it can be away from any of the design points. Right? So it's looking at how far any point in the domain of F can be away from your design points that you've chosen. And so if you want this quantity, so this quantity, the fill distance usually goes to 0, right? Or if you want it to go to 0, then you have to make sure that you choose what's called a space filling design. That's what I said here. So that means that you kind of have to put points kind of everywhere in your domain U. Right? So if there's part of U that you're kind of leaving out, then your fill distance is not going to go to 0. And so you kind of have to make sure that you put points everywhere. And in that case, your fill distance will then go to 0 with n, and you know what the rate is. For example, if you just put down uniform points or equally spaced points, then you would get this rate. Or if you sample randomly from the uniform measure, then you would also get this rate. Right. So that is where you get the convergence in n from. Right? So this term will then go to 0 as you're filling up your domain U. The rate that you get depends both on how smooth your function f is. So you see that the nu appears here, and that was related to something that we assumed on f, right? So the more derivatives f has, the faster the rate here will be, and the larger nu is. It also depends on our estimated smoothness. So the nu star here is now kind of the estimated smoothness. So I'm here assuming that the our estimated smoothness parameter converges to some nu star. It doesn't have to converge. You can also work with the lim sup and the lim inf, but that will make the result look even more complicated. So I've written it down in this simplified setting. But you can see the rate that you get depends both on how smooth your f is and how smooth your prior is, right? And you kind of get the minimum of the two. There's another term here which is related to stability. So this is actually a term which is not decreasing in n, but it's either constant or increasing. Right? And this is just related to stability issues. And so you can see that this term only comes into play when your estimated smoothness nu star is greater than nu. So that means that the prior that you're putting on f is smoother than f actually is. So you're actually assuming that f has more derivatives than it actually does have. And so you can get some stability issues in the numerical method because of that. Okay. So what exactly this rho n is here this mesh ratio. So again, yeah, it's, let me try and explain. So in the numerator, you actually just have the fill distance again. And in the denominator, you have the minimum distance between two design points. And so one way to think of the mesh ratio is just to think of the maximum distance between design points divided by the minimum distance between design points. Okay. So as long as you kind of have what's called a quasi-uniform grid, so if you think of starting with a set of design points and then kind of always uniformly refining that, then this mesh ratio will just be constant. So if you keep the ratio between the maximum distance and the minimum distance between two design points fixed, then you're not going to have any stability issues. It's just if the minimum distance between 2 points goes to 0 very fast, then you can get some stability issues. Okay, so yeah, and I mean similar comments apply to this result for the covariance. Okay. So let me briefly kind of cover the main points again. So the only assumption that you need for this to hold is that your function f that you are approximating is in the Sobolev space. So it has nu plus d/2 derivatives that are square integrable. The nu just needs to be greater than 0. So, but other than that, you can have any nu between 0 and infinity. So you need some regularity assumptions on f, but not too strong. For the estimates of the hyperparameters, you don't really have very many restrictions. So one important point is that they do not need to converge, and these parameters do not need to be identifiable. That is not an issue. The estimate of the contrast and the estimate of the length scale actually only appear in these constants. So you can see they don't appear anywhere else, so they just go into these constants here. If you want these constants to be uniformly bounded in n, so if you want these constants here to be independent of n, then you need this assumption that they are uniformly bounded between 0 and infinity. If these estimates do tend to 0 or infinity as n tends to infinity, then you can incorporate that as well. I'm happy to talk more about that. For the estimated smoothness, that is kind of the important one that goes into the rates. So the rates that you eventually get in n, those will depend on your estimated smoothness. But again, anything that's uniformly bounded between 0 and infinity is fine. Okay. In some cases, you do get optimal rates. So these optimal rates, you can think of the minimax rates from statistics. You can also view it in terms of kind of information-based complexity or approximation theory rates. So what optimal here means is that if you use any method to approximate a function f, which is in this function space, and you use n function evaluations to do that, then this is the best rate that you can get for any method that uses n function evaluations, and your f has this smoothness here. So you do get those optimal rates, in particular if you manage to estimate the smoothness correctly, and also in some other cases. And as I said, this penalty term that comes in here is related to kind of overestimating the smoothness, so using a prior that is too smooth. Right? So if nu star is greater than nu, that means that the prior you're putting on f assumes more derivatives than f actually has. Right? So then you can get some stability issues. All right. So that was this result. So what you should take away from it is that you do get posterior consistency. So as n tends to infinity, you can show that the variance goes to 0 and that the mean tends to the true function f. You don't need a lot of assumptions on the estimated hyperparameters. So the fact that you do have to estimate this and that you're doing empirical base does not really influence the result. And you do get convergence, and you do get these right-hand sides tend to 0 in most cases. Okay. So now in the end, I just wanted to very quickly talk a bit about inverse problems, because I know a lot of the other speakers are talking about inverse problems. And one of the application areas that we've looked at for Gaussian process regression is in inverse problems. So if we have the following inverse problems where, sorry, I shouldn't have used y, this is now a different y to before, but we observe some data that is of the form f of u plus eta, where eta is some noise. And what we want to do is we want to learn, or we want to find what u is given y. Then we can again solve this using a Bayesian procedure. So we will put some prior knowledge on u in some prior distribution, calling pi 0. And then to find the posterior distribution of u given y, we would then take our prior and condition it on the observed data y. Okay. So in general, in this particular setup, when the noise is Gaussian, you would then get the posterior distribution of this form here. So the posterior is proportional to the likelihood times the prior. Right. And in this setting, the map F that you have, so the observation operator, or the F that maps your unknown U that you want to recover to the observed data, that is often very expensive to evaluate or expensive to simulate. So that could involve, for example, the solution to a differential equation. So you could, for example, have this PDE here, which is the kind of steady state heat equation. So the time derivative is 0. But you would have the temperature T, so some temperature distribution on some body. You'd have some sources and sinks F, and then you would have this parameter U here, which is the heat conductivity of the body. So how well you can conduct heat. So this would be a model that you're given, and the data that you have observed would be the temperature at some points xi. And so from these temperature or from these values of the temperature that you have, you then kind of want to recover what the conductivity U of the body was. Okay. So in this case, the F of U is very expensive to simulate because it involves the solution of this PDE, because you would have to find the value of T at different points xi for a given U. Right. So in this context, you can then use Gaussian process regression or Gaussian process emulators to approximate F. Right. So you would approximate, you would compute the capital F, or directly the log likelihood phi. You would evaluate that at some design points UN, and then you can use Gaussian process regression to get an approximation. And then you can then use that and kind of plug this approximation into your posterior distribution. So in the posterior distribution that you have, you would then approximate this phi, you would approximate this F, or directly the norm that you have here, using Gaussian process regression. So that would give you something that is then a lot cheaper to evaluate. But that would then involve some error that depends on how many function values n you use. And then you can then show that the error between your true posterior that you have, so the posterior that involves the true PDE, and the posterior where you have approximated the PDE solution using Gaussian process regression, that then depends on exactly the errors that I've showed you before. So the error between the true function and the mean and the variance. And I know this was very fast. This was just to show you some applications, and you can find more details in this paper. Right. So that was really all I wanted to show. So just to briefly conclude, so in Gaussian process regression, you can get a probability distribution or the posterior distribution on some unknown function f, given n function values of f. You can then study what happens as n tends to infinity and study kind of the posterior consistency aspect, that the mean tends to the true f and the variance goes to 0. So whether you kind of converge to the truth and the posterior kind of turns to a Dirac on the truth. The reason that we have these L2 norms here comes from the application that I very briefly showed in the end. So if you do then use this to approximate the PDE in an inverse problem, then you end up using these L2 errors, but we also get pointwise errors. So if you're here interested in a pointwise error, then we do get that as well. And just to emphasize again, to get this posterior consistency and to kind of recover the truth as n tends to infinity, you don't need very many assumptions. The learning of hyperparameters in this empirical base setup that I showed you is fine and doesn't really destroy posterior consistency. And then so another way of viewing that is kind of prior misspecification, so kind of robustness to the prior. Right. So I know this is being recorded, so let me just flick through all the references so that they are on the video. And if you would like more details, then this is really the paper to look at. So thank you very much for listening, and I'm happy to take questions.
Thanks, Aretha. Another wonderful talk, perfectly timed. I'm so impressed. This session's been a dream to chair. Okay, so we're open to questions now, and I can see that messages are coming in, but I think they're all private ones to me about plans for the end of the session, so that's okay. All right, so I've always had a question in these things I've never dared ask, so perhaps I'll dare ask it now. So if I understand correctly, the function that you're referring to throughout is a deterministic function, correct?
Yep.
Okay, so is there anything useful that can be said from the approach that's being taken here about stochastic functions? Because a lot of the functions that we might be interested in are in fact not deterministic, right? Even if we pretend they are, they're not.
Yeah, so so that is kind of I think so. Usually, many people that work on Gaussian process regression, as said, they are from more the statistics literature, and there it would be the standard assumption would be that f is stochastic and that it is a sample from a particular Gaussian process. And I mean, that is really kind of the motivation for this methodology, right? So if you think about it, placing this prior on f,
yes,
kind of the same as saying I'm assuming that my true f is a sample of this particular prior.
Yes,
so that's
yes,
kind of,
absolutely, yeah.
Yeah, so that's kind of the starting point that many people have. So for these kind of results, they do hold for a particular f, and the only thing that really so if you're not estimating the hyperparameters, then the only thing that depends on f is this norm. So then I mean, you can then very easily say, if you want, then the expected value over f,
yes,
of this, if you choose the correct, so this would be finite. There's some theory that shows that. So if you take, for example, the expected value over the prior, over f, then this would be finite. If you're estimating hyperparameters, then there's the additional dependency on f in the hyperparameters, because you're estimating them from the data. Right? Does that make sense?
Yes, it does, absolutely. I'm just quite surprised not to have heard more said about that, really. I mean, because of course, being in this department, I've been to quite a lot of talks on this, and it's okay. Thank you very much indeed. Okay, so I'm open for questions from other people now, please. Again, type them in the chat, or just let me know that you want to ask a question, and we'll turn on your microphone. Okay, so Dimitris is offering one. Thank you, Dimitris. Off you go.
Thank you, Caitlin. Thanks, Aretha. Can I see perhaps slide 10 or 11, the one you were just flashing here? Right. So, so I'm looking at this result, and the convergence is in L2 sense. Is there some way that you can say something stronger, like L infinity, or?
Yeah. So in general, what you get is here you can choose any Sobolev norm up to this norm. So you can measure it in h beta. So you can measure it in h beta. So in general, you can control the function itself and up to beta derivatives. Right? And then you can use the Sobolev embedding theorem to get results in L infinity. And in fact, the L infinity rates would be exactly these. So you lose the dimension over 2 power from the Sobolev embedding theorem.
Okay.
Point-wise estimates would be these rates.
Okay, so can I follow up with this?
Of course.
So U is the domain for the parameters, correct?
Yeah.
Are you making some assumptions about it being compact or something like this, or?
Yeah. Here I am assuming that it's bounded.
Bounded. Okay. All right. And unless someone else wants to ask a question, I have another one.
I think you could go ahead since there's plenty of time anyway. Go ahead.
Okay. Can you perhaps say something about the proof? Is there, I don't know, so I haven't read the paper yet, but do I dare suspect that there is something about concentration of measure in this proof, or am I completely wrong? How do you go about proving this?
Yeah, so the main idea in proving these kind of estimates is, so if you look at this function f minus mnf, you know that this is 0 at the design point, right, because you're interpolating. Yeah.
Mm-hmm.
Right. So you know that at the design points un, this is 0, and you also know that f has this kind of smoothness.
Right.
And then what you do is you kind of know that at the design points it's 0, and then how far it can go away from 0 in between. You can bound that one in terms of the distance between the design points, which is where the fill distance comes in.
Right.
And also depending on how smooth f is, right? So the smoother f is, the closer it has to stay to 0 in between the points, which is where you get faster convergence rates for smoother functions.
Okay.
Yeah, that's
so more numerical analysis / approximation theory type of approach, right?
Yeah, yeah. So I mean, the kind of proof that you're thinking about is, I think, more the kind of classical proof technique in the kind of posterior concentration results in the statistics literature.
Yeah. Yeah. Okay. Thank you.
Yeah. So I mean, this is really a kind of specific setting where one, I'm assuming that I don't have any noise in the data. Right. So, and as Caitlin pointed out, I'm assuming that the f is a given deterministic function. So it's kind of a specific result for that.
Right.
And I'm also assuming that the design points that you choose, the points un, are also chosen deterministically. I mean, you can very easily extend it to random points, because the only thing that depends on it is the fill distance. Also this thing here.
If you choose them randomly, don't you have issues with rho? Because do you want to keep that ratio more or less constant?
Yeah, so at the moment for random points, only the fill distance has been studied. And you can show that for randomly chosen points, you still get this rate, minus epsilon, for any epsilon. After the mesh ratio for random points has not yet been studied. So that's something that I'm looking into to see. So yeah, you could have some issues there.
Very interesting. Very interesting indeed.